continuing with our Vex Houdini series. We're up on near points, so let's do it. Probably only do like a couple hours right now.
Now that we can create geometry, we continue with an addition for your tool belt. Once you have a geometry, you often find yourself that you have to isolate specific points. As with everything that we can do in Houdini, there are many ways to do this. So let me show you the few I found the most useful. We start this operation with a box. This time we use a mesh. Bring down the axis divisions to 3, and this gives us enough points to play with and dig into the following functions.
Alright. So, get rid of all this from last time. And we want to do a box. Division to 3. And we're looking at it as a wireframe, right? So I forget how to change that O up here.
At hand. This time I use color to visualize what is happening, and so we prepare the testing ground by setting all of the points to black. You can use the color node to do that, but as a short reminder, you can also do that addressing the attribute itself in the wrangle node. Which way you go is just a matter of preference.
So a color node. Color black. Or attribute wrangle. And the expression would be at CD. And then you make it a vector.
But since you want to get more comfortable with Vex, I recommend to incorporate wrangles whenever it is possible. It is a good training. Try to keep in mind that there are multiple ways to get the desired effect even when you are using wrangles. You can set the whole color vector to 0, which uses the 0 for all 3 channels. You can use the set function. You can also just deliver a single parameter. And you can use the curly brackets to fill the vector directly, but even here you can do it as a single. All of these ways have the same result. But back to the main topic. The first function I want to show you is called near point. This function uses a
CD equals 0. Near point.
position and finds the nearest point on the given geometry to that. First, we need a position. For demonstration, I want an easy way to toggle between the points, so I create a new parameter to get the point number. The value will be saved in the variable array.
Hold on one sec. I'm messing with my glasses. Hold on. So we gotta make an attribute wrangle. Integer named origin equals the chi of source. The child? CHI? Attribute wrangle connected to the color, and the vex expression is going to be integer origin equals chi source, and if we hover over this, it should say evaluates a channel or parameter and returns its value.
Origin. Generate the UI element, and let's initialize the value with, let's say, 5.
Okay, 5.
Then I grab the position vector from that point. With that, I can make the function
vector named position equals the point value.
call to near point and save the result in an integer variable.
Integer named target is equal to near point 0 position value. Near point finds the closest point in a geometry. So an integer called target equals finds the closest point in geometry.
It will contain the number of the found point. Then, to check if we indeed found something, I want to color the found points. I create a color vector and then I set the color attribute of the found point to that vector.
Set points attribute zero color data target color.
And with that point number 5 gets painted. Interesting to note,
Point number error reference to undefined variable target. Target. Okay, well I need to set this up. This wireframe goes to other objects, show all objects, goes to other objects. Shaded, hidden line ghost, smooth wire shaded. This looks like the one he's on, but I don't know why my thing's still visible. But I see there's this blue point over here, so we can see this blue point here. Looks like it's working. It's number 5. Oh, it's because we set it to be 5. I see. It's probably hard to see on stream, but you can see it's changing. How do I get it to be like this? I don't know.
If you only put one value for the color vector, it only fills the first element, unlike the handling that I showed you before. But since I wanted to use red anyway, this is fine. If I now move the slider for the source, other point as nearest point. Obviously at the position of the point itself is the nearest one. If we take a look at the top of our box, we can see that point 19 is in the center. When we choose it as our source, we see that only point 19 distributes the color red. And so it does. That's pretty handy, but most of the time you will need an external position as source. So let's create that setup. Alt click and drag the wrangle, and then I create a primitive sphere which only has one point that can be tested. I don't need that one anymore, so bring in the sphere and we'll make it a bit smaller. Since the size of the sphere doesn't matter, we only need the point in the center. Then connect the sphere to a transform node. And push it a bit higher. Next, the transform node goes into the second input . We only need to make a simple change in the code. Instead of using the slider value, we use the first and only point that comes through the second input. Now select the transform node and move the sphere around. As you can see, the function uses the position of the sphere closest point on the box. An important observation to make with this function: we want to find the nearest point without any restriction on the distance. No matter how far we take the sphere, there's always that is nearest to it. Another way of searching for points, function near points. Similar name, but works in a noticeably different way. Let's clean this up a bit. We want to keep the origin from the source and also the position. Then we need another parameter that defines the distance that we want to search. Again, generate the UI element and let's initialize the value with 1. Then go back to the editor and we can now make the function call. Instead of a single point, this function returns an array of points. So we need to write the result into an array variable points with this. Let's clean this up a bit. We want to keep the origin from the source and also the position. Then we need another parameter that defines the distance that we want to search. Again, generate the UI. Element and let's initialize the value with 1. Then go back to the editor and we can now make the function call. Instead of a single point, this function returns an array of points. So we need to write the result into an array variable, targets, and then provide the starting position. And then the max distance the function is going to look for points. Now we can go through all of the found points with the for each loop and set each of those points red. Again use setPointAttrib, and again since I want the color red, I just type 1 for the color vector. As you can see now, we have a whole area of red points. We can still change the origin, how big the affected area is. To make it a little bit easier to see, I create a second box with a lot more divisions and connect this one to the color node. And how the function has its center at the source and how it travels the provided distance to find all the points that are there. Apply the idea of the external position. We only need to change from where the origin position is coming from and then connect our sphere again to the second input of the wrangle. And again we can control our found points with an external position. Here to find all the points that are there. Second input of the wrangle. The next option is the neighbor function. This one is more suited to explicitly search points on the same geometry. Again, we need an origin point and then an index that defines which neighbor we want to address. But let's start from the beginning. First we need a new integer parameter for the index of the neighbor. And then an integer result for the neighbor function. The function itself only needs the point number of the origin and then a designated variable for the index. Generate the parameter and I set this one to 4. I tell you that was found. And as you can see, there is no point painted. And I say explicitly painted and not found, because the function itself does find points. Let me demonstrate that with the smaller box. If we look at the point 19, the possible neighbors are 20, 7, 18 and 16. The points 17, 6, 8 and 15 are not directly connected to the origin point. Therefore, the function only finds 4 points and it begins to count with 0. That being said, if I pick the index 3, the point 7 gets found. So basically the function neighbor lets me address a specific neighbor of the original point. But this is a very special situation. Most of the time you want to address all of the neighbors. And of course, there is a function that is called neighbors. This function allows you to do exactly that. So let's reopen the edit.
Did I get this right? Let's see. Integer, origin, source, integer, neighbor. Targets equals neighbor. How come it doesn't show up as a Oh, this is not the same one. What am I editing? That's why. That's why I was using the other one, or the wrong window. Int ne equals a integer called targets is equal to neighbor 0 origin set points attribute 0 cd targets 1 set. So there you can see it selecting in different points.
And make a few adjustments. We don't need the neighbor index anymore, and we can also delete it from the function call. And like the function near points, this function also returns an array. Then we can loop over that array, again with the array loop function for each, int pt for the array element and the array itself. Before we saved one specific neighbor in the variable targets. Now targets is the whole array, so we have to change the function call of setPointAttrib from targets to pt. And as you can see now, all of the neighbors of the source 19 are painted red. If I change
okay, error pt source. Targets, neighbors.
Change the source selection, a whole new set of points gets painted. For a clearer image, let's connect the box to the network that holds much more points. This makes it much easier to see which points exactly are selected as neighbors. Let's pick a point from the top as our source. 280 should be right up here. And now it's very obvious which points distribute the color red, because they are the direct neighbors of the point 280.
Okay. Alright, cool. Moving on. Point clouds.
And last but not least, another function I like to use is called point cloud. Point clouds are a bit different. The function PCOpen opens a point cloud file and queues up access to the points in that cloud. The points contained in that cloud are based on an original point position and a given distance. So let's adjust our coding accordingly. We need a variable for the distance we are going to search, a variable for the amount of points we want to save, and we still need the int variable target.
float called distance is equal to. So these things in the green parentheses, like dist, amount, those are actually linked to parameters, right? Like they're actually names for, it's like pulling the distance from Houdini, right? And then this amount is actually pulling an amount, right? Like, what would you call these? Evaluate to channel. Is this a channel? Let's check the manual channel. Channel list, channel nodes. The channel list lets you work with parameters and makes it easy to edit values and channel groups and manage the currently scoped parameters. The channel group list shows all channel groups. Press right click on a group to see a context menu for the group. The parameter list shows the parameters on the selected objects and or in the selected channel groups. Select parameters in the list to scope them. When you select objects, the channel list shows parameters of the object that either are keyed already or are marked autoscope. Autoscope is a property of commonly animated parameters that makes them automatically show up in the channel list. In addition to the value editing techniques and shortcuts available in the parameter editor, you can also select multiple value boxes at once in the parameter list and type or use the middle mouse value ladder to change them all at once. Press right click in one of the subpanes to show commands and options specific to the subpane. Press right mouse on items in the list to show the command. Okay, where is that channel list? Distance. ABS. So these are all the channels that you can get values from. And there's so many of them, right? Black body. Bump map. Curl noise. Okay. Back to the tutorial. So the next part is integer targets equals function of neighbor. Result of the neighbor function. Set point attribute to 0, color data, targets 1, set. Okay, so go ahead.
Let's clean this up and delete the neighbor function. And to start with an error-free scenario, let's also delete the setPoint attribute and code this from scratch. Since I want to use an UI to control my function, I have to now initialize these parameters. For now, let's set the amount to 3 and the distance to 2. It will make sense soon. Then we can go back to our editor and write the logic around a point cloud. Again, we start the same way. We take the position of our original point and then we open the point cloud by setting the starting point to that position, look for the distance we defined, and then save as many points as we defined in the variable amount. Now one of the
Okay, so here he's making a vector named position, and that is equal to the result of the point function. Zero P for, is there like a way to look at the list? The channel, the parameters. Parameters group method. Attribute. Are they attributes? P point position. The viewport uses this to lay out the points of model 3D space. Common attributes. Attributes are named values stored on vertices, points, primitives, and objects. Point color, position, coordinates, spline weights, and normal, for example, are stored as point attributes. Primitive, point, vertex. So common ones, shader overrides, diffuse color override, color diffuse, 3 vector, a vector 3, the viewport uses this color, OpenGL geometry, alpha transparency override, float value, point position, okay, so a vector called pos reads point attribute value from geometry. Point origin. Source. So what is source? Okay, coolly. So, and then it makes an integer called pcloud, which is equal to the result of the PC open function. Returns a handle to a point cloud file. 0 point positions. Okay.
Big differences with point clouds is that you have your own set of functions to work with them. For example, we now can check if our point cloud has found any points. We can do that by using the function PC_numFound. Provide the handle to the point cloud, and if this function delivers anything above 0, it has found exactly that amount of points. We can then loop over the found points with the while loop. As condition for the while loop, we provide the point cloud function PC_iterate. The function will grant access to the first point that is nearest to the original position. It will continue to do so until it reached the farthest point, and then the while loop ends. While we are in one iteration, we have access to all the information of that point. We can now use the function PC_import, use the cloud handle, and for example access the point number. The function writes the result into the variable target. This might look a bit weird since we don't have the target variable on the left side then equals the function, but just remember the principle copy by reference and you understand how it works. But now that we have the point number of a point that's found in the point cloud, we can now again use the function setPointAttrib to paint it red. And we can't see anything because probably our sources on the other side of the box. Yeah, let's again use our sources on the other.
It goes so fast. It's like edited quickly. Set. Okay.
Red. And we can't see anything because probably our sources on the other side of the box. Yeah, let's again use the source point 280.
Do I have an error? It doesn't say I have an error. But I probably do have an error. PC. There we go. Okay, so there's the source. Very good.
PointAttrib to paint it red. And we can't see anything because probably our sources on the other side of the box. Yeah, let's again use the source point 280. And there we have some red color. Now, why are these the points that are inside the point cloud? There are much more points around the point 280 in a distance of 2. But as you may have guessed, we set the amount of points that can be in the point cloud to 3. So it would make no difference if we increased the distance we are looking for. In this case we have to increase the amount to grab more points. And that will put all of these points into the point cloud. If we now on the other hand keep the amount high but shorten the distance, it will once again ignore all the points that are farther away from the point 280. Now why would you use the function pointCloud if you just could use the function nearPoints? It would deliver the same result.
Point cloud seems like it has more.
One argument for point clouds would be the flexibility that comes with it. The details around point clouds could fill another module. But there are tools built in the concept of point clouds like the function PC_farthest. This function grants you access to the point that is farthest to the original position. And if you remember, this must be the point that's the last, which will be delivered by the function PC_iterate. I just saved that value into an detail attribute, and knowing where the farthest point in the cloud is opens up a lot of opportunities. And as we did with the nearPoints function, we can also use the point cloud with an external source. Again, we make a copy of that wrangle and then connect the transform from the sphere to the second input. And this time the only thing we need to change is the input from where the original position comes from. And again, we only have one point on the sphere, so set this one to 0. We can now go back to our transform node and start moving around the sphere and thereby controlling which points are inside of the point cloud. You might not realize it, but this is one of the more important concepts you have to understand. Being able to isolate specific points by using wrangles allows you to keep every workflow procedural. Once you do it manually, you run in danger of breaking the procedural chain. So keep that in mind.
Okay. It's good to know. I'm starting to understand the syntax a little bit better. Like, I think was it yesterday? No, the day before I was doing this. And I was getting kind of lost, but now I'm understanding. So he's defining a variable, which is a vector, called position. And that variable is equal to the result of the function, of the point function, which takes these inputs. And you can look at the documentation for this. So it doesn't crash. And then it shows you how you have to set up the point function. So you have type points, then you have geometry, string, and integer. Geometry when running in the context of a node, such as a wrangle, SOP. This argument can be an integer representing the input number starting at 0 to read the geometry from. This is the wrangle. This argument can be an integer representing the input number. Oh, okay. So it's saying input 1. Well, input 0. 0, 1, 2, 3. So it's taking the first geometry and then the string P, which is the point data, right? String attribute name, the name of the attribute, or intrinsic to read. So you're reading the point data, right? That's what P is. And then origin is the point number. The point number to read the attribute on. Returns the value of the given attribute on the given point number. Or 0 if the attribute or point does not exist. Okay, yeah, I'm starting to understand it a little better. It's making more sense now. So let's go to the next one. I think I got maybe one more in me and then I might be done. Point clouds, so we did that. Manipulation.
In this clip, we use the mechanics of searching the points on our geometry to control manipulation of the found points. Once you can isolate the points, you are able to do all kinds of things with them. Change attributes, move them from their position, or delete them if you don't need them anymore. We set this up in a very similar way as with the searching. First we create a primitive sphere, and I will use it as a trigger for the manipulations. I decrease it in size just...
Okay, sphere size is 0.2.
Just a bit. Again, the
Transform.
origin of the measurement will be the point in the center of the sphere, connected to a transform so that we have a handle for the coming steps. Then we need to create some points. For now, let's help ourselves with a grid that is set to points. Increase.
Move. Okay. So then we make a grid.
Rows and columns so that we can see what is happening with the points. Now we could use several methods for this step, but I like to use the point clouds in this case. So create a wrangle node and connect it to the grid. Then we take our sphere and throw it into the second input. Let's open the editor and start coding. We need an int handle for the point cloud, and we open it based on the second input and the position of the currently tested point of the grid. We search with a radius of, let's say, 2, and we only need to look for one point. And again, we need to use the position information of the sphere itself. So grab that with the point function. And as a next step, we need to create a direction vector. My goal is to use the sphere to push away the points of the grid. That means each point needs to have a direction where I can push it to escape the sphere. And I can get such a direction by subtracting the position of the sphere from the current point in the grid. Now to the logic.
Okay, so he said that make an integer called PC Cloud. PC Cloud, point cloud, integer point cloud. Point cloud is equal to the result of the PC open function. And PC open takes what? So this function opens a point cloud file and queues up access to the points contained in it. You can then iterate over the points with PC unshaded or PC iterate. The first two versions of this function queue up points centered around a certain location P within radius based on point positions found in P channel. Only the max points, closest points within the given radius, will be queued. When using PC open with PC iterate, points will be sorted from nearest to farthest. The file name may use the OP syntax reference SOP geometry in the OP context. The P channel parameter indicates the channel in the texture which contains the positions to be searched. P channel will be made read only if it is not already blah 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 blah. So it says integer name PC open, file name channel shaded. So he's opening up one, file name 1. P channel is P at P vector radius 2 max points 1 vector name position and getting the position data of each point, and then vector is the at P minus position. Okay.
Logic itself. First we check the point cloud if it found the point. This means every single point of the grid does this test for itself. Now add the direction value onto the point position. Then hit apply and we got an error. And there you have it. Even a single missed comma can break your code. The code is working, so let's move the sphere and check out what we got so far. Now there's definitely something happening, but it's a bit weird. All of
point cloud, point cloud. See the found.
So let's move the sphere and check out what we got so far. Now there's definitely something happening, but it's a bit weird. All of the affected points are moving in unison in one single layer. That was not my goal here. So let's find out what is missing in this setup. First, let's make it a bit more visible by increasing the point size in the viewport. Then go over to the Visualizer tab and create a new marker. Call the...
Hold on, bro. Wait, where's the... Oh. There, now I can move it. It's not moving my points though. It's not moving anything like in his.
And check out what we got so far. Now there's definitely something happening. The code, even a single.
Let's go back and check the code. Integer, point cloud. Let's see what the. Oh, here we go. Plus minus. Now we should have something going on. There it is. Yeah, that's definitely something.
Missed comma can break your code. The code is working, so let's move the sphere and check out what we got so far. Now there's definitely something happening, but it's a bit weird. All of the affected points are moving in unison in one single layer. That was not my goal here. So let's find out what is missing in this setup. First, let's make it a bit more visible by increasing the point size in the viewport. Then go over.
Point size in the viewport, where is that?
First, let's make it a bit more visible by increasing in unison in one single layer. That was not my goal here. So let's find out what is missing in this setup. First, let's make it a bit more visible by
You did a shortcut. Viewport. Display options.
increasing the point size in the viewport. Then go
Geometry, point size.
over to the Visualizer tab.
Visualizer.
And create a new marker.
New
Call that marker Deer for direction all the way through. And then set the type to vector trail.
Vector trail.
Now go back to the wrangle and write the direction vector we created as an attribute onto each point. When we hit apply, you will see a yellow trail from each point that marks the point where it started to the point where it's now. When we take a look at the geometry spreadsheet, you will see that there's in fact the direction vector on each point. So that's why we can see the yellow trail. But as you can see, all points that can find the sphere gets pushed in unison because we use the distance between the sphere and the point to determine the distance it travels. When we place the sphere directly onto the grid, it first looks as if they do not move at all. They do move, but they move parallel to the grid. But this is not the behavior I'm looking for. The points that are close to the sphere barely move since the direction value is the representation of the distance between them. If you want to make sure that the direction you created is in fact a direction, you need to normalize it. So let's copy this wrangle and make that adjustment by writing a normalize in front of the calculation.
Normalize, you say.
Now each point that finds the sphere moves 1 unit in the direction. This gets closer to what I have in mind, but it still looks pretty weird when the sphere approaches the grid. The points jump to their designated positions as soon as the range of the point cloud hits them. But when we take a look from the top, you can at least now see that all of the points are moving. What we need here is some kind of fall off that helps to make the transition. We only need to add a little something for that. So let's make another copy of this wrangle node.
Why? Why does
We
it make
need
copies?
2 more variables. We need the distance between the sphere and the points and the mentioned fall off. In the end, we are going to use the variable fall off to multiply it with the
float vector, or an variable, float variable called distance is equal to 0. Float variable called fall off is equal to 0.
direction. So let's start by throwing that in there. But to create the fall off, we need the distance between the 2 points. There is a function that delivers exactly that, and it is also called that. We can use the function distance to get exactly that from 2 positions. Now this is an important concept to understand when working with from 2 positions. Now this is an important concept to understand when working with vectors, and especially if you start moving them around in a big scale with your wrangles. When we set the multiplier fall off on 1, we don't change anything. If you use the distance as a multiplier, we're back at the unnormalized direction we created in the first place. As you can see, there's no difference when I change the flag between those 2 nodes. But these are the values we need. We just have to fit the range of our distance to something else. When the sphere is far away, the multiplicator needs to be small and therefore only moves the point by a small amount. When the sphere is very close, we need the point to move far, so the fall-off multiplicator needs to be big. That being said, we need to use the function fit. The function allows us to take the original range that was 0 to 2, since that was the range of the point cloud, and convert it into a new range. This new range needs to be reversed. So if the distance is 0, we want the multiplicator to be 1. And if we have the max distance of 2, the multiplicator should become 0. And now we should have a smooth transition depending on the distance between the points and the sphere. When we now move the sphere through our grid, we should see a very smooth movement from the points.
Coolie! Dope. Sick. Sickness. Well. This one down. Alright, I gotta dip out. Because late here I might work out. I might go to bed. We'll see. But definitely gonna continue with this Houdini series. Still got 20 plus more, 30 plus more lessons to go. About like 40 more lessons. So should be a good series. It'll probably get pretty in depth. Pretty cool. I don't really see myself using the code. I mean, maybe as I keep going on, it'll become more apparent how I can use the code, but yeah, man, Houdini is just so much more versatile than any other program I've used. Like even After Effects has expressions, but those don't seem as deep as the Vex stuff in Houdini. Seems crazy. Like just looking at the manual, it's like goes so deep. All right, I'm out. Peace.